And we're back in the SimkinsPhysicsCorner, having good times. It's game time, ready for the AP test coming up in May. Well, today's topic is kinematics. We're going to look at two problems, two parts of this video. So this is part one. Let's dive right into it with our handy equation sheet, compliments of the College Board, and our calculator. Make sure you're ready for game time. Let's take a look. Toy car experiences an acceleration of 0.5 meters per second as it drives up a ramp. So we're driving up a ramp. After traveling along the entire ramp for 2 meters, I'll draw my little toy car here, experiencing an acceleration of 0.5 meters per second squared up the ramp. It leaves the edge of the ramp and drives off the table. Okay, so I guess our ramp is on a table, and our table might look something like this. There we go, sweet. If the table is 1 meter high, label this guy 1 meter, and the ramp is angled at 30 degrees relative to the table, how far from the edge of the table does the car hit the floor? What is the maximum height above the floor that the car reaches? So the car is going to start over here at rest. It's going to accelerate, gain speed up the ramp. So for the first section up the ramp, we just have a very straightforward linear acceleration type of problem. And then we're going to launch into what would be considered an angled projectiles problem, because the car is going to drive up off the ramp, go flying through the air, and hit the ground somewhere over here. So the question is asking how far from the edge of the table. That's delta x. That would be from the edge of the ramp or table there. That would be this distance. That would be our delta x. And it's asking what is the maximum height that we reach. Delta y as we fly through the air. You guys see that? Okay, I'll zoom in just a little bit. There's our drawing. All right, so we've set everything up. We got all of our knowns listed. Let's go ahead and dive into the first part, because before we do any projectile motion, we want to know this overall velocity right here, and then we're going to break it down into its component velocities as well. So let's figure out how fast the car is driving off of the edge of the ramp in the direction of the ramp. All right, so that information would be acceleration is 0.5 meters per second squared. Our theta is 30 degrees, and our delta x is 2 meters. Now we know our initial velocity is 0 because we start from rest, and our goal is to find that final velocity. All right, so let's look at our kinematic equations. I don't see any time in here. Okay, so right away I'm going to rule out equation number 1. I'm going to rule out equation number 2. Let's see if equation number 3 has anything to offer us, because it does not include time, and we happen not to know time. So let's go ahead and write this down and see if that gets us anywhere. V final squared equals V initial squared plus 2a delta x. All right, so I found that on my equation sheet. The reason I'm using it is because I don't know time, and we're going to see if this gets us anywhere. V final squared, that's what's staying, that's what we're solving for. V initial is 0, and we're going to plug in our stuff over here, and our delta x is 2 meters. Oh man, these numbers way too easy. So we got velocity final squared equals 2 times a half times 2. That's going to be 2, but don't forget to take that square root. Final velocity is square root of 2 meters per second, or, dropping my calculator here, make it a decimal, 1.414 meters per second. What did we just solve for? We just solved for this, the velocity that the car is traveling as it leaves the ramp. Now, keep in mind, it's not horizontally driving off the ramp. It already has momentum in that upward direction, so it's going to continue in that upward direction as it flies off the ramp. Okay, part 2 of the problem. Now we're in projectile mode. Okay, so anytime you have a projectile problem, right away, the first thing you want to think about is, how can I separate the x and y motions? We know for projectiles, the motions in the x and y direction happen separately, or I should say they happen independently, but simultaneously. Meaning, like 9.8 doesn't affect the horizontal motion at all, right? Because 9.8 is the vertical acceleration due to gravity. They happen at the same time, simultaneous, but they don't depend on each other, because the force of gravity doesn't impact at all the horizontal motion. So let's go ahead and break up the x and y motions here. I like to use the strategy of what I call the XYT table, or you draw what you know in the x and what you know in the y. Okay, I mean, we separate this. So we always know in the y that g is negative 9.8 meters per second squared. Looks like we're going to need to know this little height, h. I'll call that height h, because the car leaves from up here. All right, so the car leaves this 1 meter and whatever this height is. Okay, so real quick, with a little bit of trig, we have this angle, so theta equals 30. This would be considered the opposite angle because it's opposite that 30, so this is our opposite side. And opposite SOHCAHTOA would tell us to use sine. Sine of what? Oh, the hypotenuse here is 2. So this is the hypotenuse. This is the opposite side. So to find that little extra height there, the hypotenuse would be, the height of the opposite side there would be 2 sine of 30. And I'm sure most of you guys got that really quick. Hey, it's 1 meter. Oh, I love these numbers. Because what that tells us is that this initial this initial height, I'll put an I there, is 2 meters. That's the initial starting height of our car as it drives there. It's 2 meters off the ground. And, of course, our y final, this is where choosing your coordinate system is important. But we'll call our floor y equals 0 because that's a nice thing to do. All right, we'll call that y equals 0. We don't know too much else about the x. We don't have any idea about this yet. And so remember, they happen independently, and the x and y motions happen independently but simultaneously. Let's try to get time. Don't know much about x, but anytime you start a projectile problem, the first thing you want to do is get the components of the velocity. Our components here, you can either do the trig, or you can just remember Vx equals V cosine theta, and Vy equals V sine theta. Okay, you can do the trig, or this is one thing that we just memorized in class: y sine. So Vy here is going to be the overall velocity, 1.414 sine of 30. The reason I know it's 30 is because if the ramp is oriented with a table at 30 degrees, by the time we get up here, there's some kind of geometrical theorem that tells us that if we draw a parallel line to the table, this is going to still be a 30-degree angle up there. So we still use 30. And 1.414 sine of 30 gets us a Vy, a y component velocity of 0.707 meters per second. And I'm also going to write Vy initial because that's how fast we're traveling in the upward direction as we leave the top of the ramp. Do a similar thing for x. So we're going to have 1.414 cosine of 30. 1.414 cosine of 30. And our Vx is going to be 1.22, which makes sense because at 30 degrees, we're going more horizontal than we are vertical. All right, that's why this number is bigger than this number. All right, well, we got quite a list of knowns now. And as you can see, the side that we know the most about, the direction we know the most about motion, is the y direction. So we take it back to our equation sheet again. All right, I don't know time. I'd really like to find it, though. So first I'm going to look at the equation of time and see if I know enough information to get stuff out of that. But you'll also notice as you take a careful look at our knowns, we don't know v final y. And that would be like how fast are we going downward when we run into the ground. So we don't know v final, and we don't know the time. We sure would like to know the time, though. So I'm going to rule this one out because it has a v final right here. That's v final. That's the time. So I can't use the first one. Let's see, the second one. I know, and remember, we can switch out x's and y's. These generalized equations work in both directions. The equation sheet just happened to write them the horizontal version. We can do the exact same equation vertically. We know y final. We know y initial. We know v initial y. We don't know t, but that's the one thing we're looking for. So far, we're only short one variable, and it's looking good because that's the one we want, right? 1/2 a, we do know the acceleration in the y direction is 9.8, and t is the unknown as well. So this is how you select your equations. You ask yourself, what do I want? It'd be really nice if we could get t. And then you look at the side with the most information and determine if there's any kinematic equations that can help you solve for that thing you're looking for, in this case, time. So I'm going to go ahead and write this kinematic equation down, but in terms of y, y equals y initial plus v initial y t plus 1/2 a y t squared. And some of you can already tell that we are going to run into a quadratic formula type of deal. Good thing we have our graphing calculator. More on that in a second. Let's plug things in. Y final is 0. You have to be very careful about your coordinate system and which way is positive. We're going to assign up as positive and down as negative. Okay, and the reason we need to do that is because here we got 2 meters. V initial y is in the positive direction because we're moving upwards as we leave. So that's going to be 0.707 times t. That's a t. I got to make sure it doesn't look like the same thing as a plus sign. There's a plus sign. 1/2. Now this is important. Negative 9.8 t squared. Okay, the acceleration is down, so we got to stick to our coordinate system that we've chosen. All right, well, here's the cool thing you can do. If you type this into your calculator, anytime you get a quadratic equation deal like this, all right, let's see, we have 2 plus 0.707, and you can hit this little X key right here. Okay, that's our variable time that we're looking for. Plus, half of 9.8, many of us have that memorized now, is negative 4.9. And then I'll do that times x squared. Okay, so if you look carefully here, you set this equation in your graphing calculator and you graph it. Now what we're looking for is a solution where it crosses the axis, because wherever it's equal to 0, that's where our solution is going to be. So I'll zoom square. Let's see if that helps us at all. Not really. Let's try zoom box. Can we get any closer? And you want to hit the trace button, and that'll help you trace this guy. Alright, so we can see what's going on here. It'd be really nice if I could see what the heck's working here. Oh, now we're getting somewhere. I can kind of see that function a little bit better. Let's keep zooming in. I must have been doing some big old functions before. Alright, so hopefully your calculator is set up a little bit better. Sometimes it's a trial and error. There we go. We're looking for where this guy crosses the, we're looking for where it crosses right here. Obviously you can't get a negative solution for time. So wherever this equals 0 is where our time is going to be. So you hit the trace button, you go left and right, and then what you can do is you can say second calc, see the little yellow up there, and we want to calculate to find where the 0 is of this function. So press enter for the left bound, press enter for the right bound, and select a point in between, and it's going to solve that equation for you. Now, could you do y equals negative b plus or b squared plus or I don't feel like looking up the formula. I'm going to use my calculator. All right, so the time here we get is 0.715 seconds. Okay, well that's not really what it asks us for, is it? Because this is useful. It's useful information. But the question is asking how far from the edge and how high. The nice thing about projectile motion is that the moment the car leaves the ramp here, the amount of time it takes to travel up and then down is the same amount of time it takes to travel out. Okay, because the x and y motions happen independently but simultaneously. And so that time is 0.715 seconds over here, and I'm just going to wrap this up because the first question is how far from the edge of the table does it land? So this isn't on your equation sheet, but by definition, velocity is the change in x over time. So I'll write that over here. Velocity x equals change in x over time. And if I solve that for x, it'd be delta x equals vx times t. Vx, we're going to pull from what we did earlier, 1.22. And time is going to be right here, 0.715 seconds. And if we do that, go back to the calculator here, 1.22, 0.715. That's going to get us a distance of 0.8723. Probably don't need that many decimals, but we'll hold it. That's our range. So that answers the first question. How far from the edge of the table does the car hit the floor? This next one, what's the maximum height above the floor the car reaches? There's a couple of strategies you can use here. If you consider the motion here, it's going to leave this spot and it's going to go up until it reaches this point. Now we know at the apex for a projectile, the Vy equals 0 at the apex. Alright, so we could do something with that. We could also take a look at our equation sheet because maybe there's something in here now that we know the time, now that we know some more things. Maybe there's a way that we can solve for that other variable. For instance, if we take a look here, we can probably calculate the height that it raises off of the ramp. So let's think about this approach for a second. We're going to solve the problem such that we have an initial upward velocity, and we know that up here we have no upward velocity, right? So we're basically just going to solve how high did we raise here. And since we know the height of the table and the height of the ramp, or I used to say the height that the ramp gives us, if we can just solve for this little bit right here, then we can add that to our 2 meters and we'll have our final answer.